Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Our objective is to take a brief look at the relay. A relay is an electromechanical switch that serves as the principal logical element for an electrically controlled system. In contrast to the contactor, a relay is traditionally designed to establish or interrupt low voltage control or pilot signals only, and not high voltage, high current power input used to run an industrial motor. Relay contacts seldom directly switch primary loads like motors or pumps, and only do so in the lowest of low-power applications. Relays typically switch pilot or control signals to other pilot devices like the coils of contactors or the solenoids of hydraulic valves. Devices like contactors or solenoids, when commanded to do so by the pilot signal, do the actual conduction of primary electrical or hydraulic power. Similar to the relay's big brother, the contactor, a relay also has a coil and associated contacts. The principal difference being these contacts are traditionally rated for low voltage control signals only. Relays are used in applications when it is necessary to control a circuit with a low voltage control signal with complete electrical isolation between the control and power aspects of the system, or where several circuits must be controlled by one signal. Relays can perform numerous functions and coordinate the activity of a complex system because a relay traditionally has available not only normally open contacts that close when the coil is energized, but also normally closed contacts that open when the coil is energized. These contacts can be used within the logical framework of an electrically controlled system to selectively energize or de-energize other elements within the system or between two separate systems at the appropriate moments to coordinate and sequence activity. Additionally, timer and counter relays allow time and repetition-based functions to be incorporated into an electrically controlled system. We'll look at timers and counters and even solid-state relays with no moving parts in later lectures. Today's lecture deals exclusively with general-purpose electromechanical relays. Relays come in several forms, the two most common being the industrial or mini contactor relay, since it looks like a mini contactor, and the plug-in or ice cube relay, since it looks like an ice cube. Ice cube relays come in many sizes, and it's a recommended practice to not put them in your drink. An ice cube relay has a matching keyed base into which the relay fits. The base is hardwired to the system, and the relay can be removed for inspection, maintenance, troubleshooting, or repair purposes. Sometimes plastic hooks lock the relay into the base and must be unhooked for the relay to be removed. Don't be the guy that rips a plug-in relay out of its socket and hears broken plastic pegs tumble into the equipment you're working on. The back of the bases typically clip into a rail. In contrast, an industrial relay is typically directly hardwired into the system. Just like the contactor, a relay is typically characterized by a set of moving contacts that make or break a connection when commanded to do so by an electrically isolated, low-power control signal provided to the coil. Sometimes these contacts are electrically isolated single-pole, single-throw switches, as is typical for an industrial mini contactor relay. Sometimes these contacts are single-pole double-throw switches, the shared common terminal, as is typical for an ice cube relay, sometimes called C-form contacts or transfer switches. Can you see why they're called C-form contacts? When one side is open, the other side is closed, and vice versa. Manufacturers sometimes use a single-pole double-throw switch symbol to make the transfer function readily apparent. This is the IEC schematic symbol for an ice cube relay. You can see the similarities. This is the coil. This is the common side for two single-pole double-throw switches. This is the normally closed side. This is the normally open side. The IEC schematic symbol makes it very clear the switches are controlled by the mechanical interlock with the coil. In either case, the switches are isolated from each other, and the switches are isolated from the coil. In its deactivated state, the normally open contacts are open and do not allow current flow, and the normally closed contacts are closed and do allow current flow. In their activated state, the normally open contacts close and allow current to flow, and normally closed contacts open and do not allow current to flow. A disclaimer before we continue. Always consult the manufacturer's datasheet for the specific relay of interest. Do not for a moment assume the pinouts and specifications presented herein are universal in nature. A thick, tangled jungle of not only NEMA and IEC differences, but also manufacturer-specific pin numbers and idiosyncrasies exist, especially for older relays. This being said, most manufacturers now offer dual NEMA and IEC numbering schemes, with the IEC numbering scheme becoming more and more accepted because of its standardization and ease of interpretation. The IEC terminal numbering scheme uses 2 digits. The first digit is the specific switch. For this schematic symbol of an industrial mini contactor relay with 4 electrically isolated switches, 2 of them being normally open and 2 of them being normally closed, this is the first switch. Each terminal of this specific switch is assigned the first digit of 1. The second digits indicate the function of the switch. Normally closed switches are assigned a 1 and a 2. Normally open switches are assigned a 3 and a 4. Since this first switch is normally opened, these terminals will be 1, 3, 1, 4. This is the second switch associated with this relay. Each terminal of this specific switch is assigned 2 as a first digit. Since this second switch is normally closed, these terminals would be 2, 1 and 2, 2. This is the third switch associated with this relay. Each terminal of this specific switch is assigned a 3 as the first digit. Since this third switch is also normally closed, these terminals would be 3, 1 and 3, 2. Finally, this is the fourth switch associated with this relay. Each terminal of this specific switch is assigned a 4 as the first digit. Since this fourth switch is normally open, these terminals would be 4, 3 and 4, 4. Any auxiliary contact blocks added to this relay would continue this scheme starting at 5 for the first digit. Ice cube relays with single pole double throw switches use a similar numbering scheme. The first digit is assigned the number of that particular switch. This is the first switch associated with this relay, so each terminal's first digit would be 1. The common terminal's second digit is 1. The second digit is indicative of a switch's deactivated state, similar to previously. A normally closed switch is assigned a 2 as a second digit. A normally open switch is assigned a 4 as a second digit. The terminals of the second switch associated with this relay would be assigned 2, 1 for the common, 2, 2 for the normally closed side, and 2, 4 for the normally open side. Alternate representations of the schematic would use the same terminal numbers. Any additional switches associated with this relay would continue in this same fashion, starting at 3 for the first digit. If you're ever lost about which pin is which, just look at the manufacturer's datasheet or on the side of the relay itself. Very often the pinouts are printed on the side as well as pertinent electrical data. Coils are normally designated A1 and A2. The coil is supplied the low voltage control signal, which could be 24 volts DC, 24 volts AC, or 120 volts AC as representative examples. DC coils with freewheeling diode arc suppressors are polarity dependent and must be connected with the correct polarity. If a plug-in ice cube relay has 2 coil terminals and 2 3-terminal single pole double throw switches, this means it has a total of 8 terminals. These are sometimes called octal base relays. Think octopus. Note the key on the plug and the socket and the dual numbering system. NEMA on the inside and the IEC on the outside. If this relay is inserted to the socket correctly, the 2 outside terminals on the bottom of the base are the 2 coil terminals A1 and A2, and the 2 middle terminals on the bottom of the base are the common terminals for the 2 independent switches 1, 1 and 2, 1. The 2 outside terminals on the top of the base are the normally open switches 1, 4 and 2, 4. The 2 inside terminals on the top of the base are the normally closed switches 1, 2 and 2, 2. Keep in mind we're looking at the base, not the bottom of the relay. If you look at the bottom of the relay, you've got to do a 180-degree switch on the vertical axis of the key. Other configurations exist. If we added another 3-terminal single pole double throw switch, this would be an 11-pin relay and obviously require a matching 11-pin base. The base for this specific 11-pin relay has the commons for all 3 switches on the row above the coil, the normally open terminals for all 3 switches on the row above the relay, and finally the normally closed terminals for all 3 switches on the top row. Note the dual numbering scheme is thankfully printed on the outside of the base. Additionally, tab-based ice cube relays exist. This is an 8-tab relay with an 11-tab base. This specific base has the commons for all 3 switches on the top row, the normally open terminals for all 3 switches on the middle row, and finally all the normally closed terminals for all 3 switches on the bottom row. Note the dual numbering scheme. Additionally, they're nice enough to explicitly print common, normally open, normally closed, and coil right on the base. If this 8-tab relay was used in this 11-tab base, the terminals for the middle switch 2 just wouldn't work. The state of the coil inside a relay is the determining factor whether a particular switch is in its deactivated or activated state. The coil is part of another electromechanical device known as a solenoid. A solenoid is an actuator, a term that means a device that takes one form of input and converts it into mechanical movement. In this case, the solenoid converts electrical energy of the control signal to linear mechanical movement via an armature. When the coil is energized by a low voltage control signal, the armature is pulled towards the coil and the contacts attached to the moving armature change from their deactivated to their activated or opposite state. One can see the actuation mechanism internal to an ice cube relay. When de-energized, the spring pulls back on the lever and the common in the center is making contact with a normally closed contact at the top and disconnected from the normally open contact at the bottom. When the coil is energized, it pulls the lever arm down and the common in the center is disconnected with the normally closed contact at the top and making contact with the normally open contact at the bottom. This is associated with a characteristic audible click that can be endearing or equally maddening depending upon the application. Solid-state relays, as we'll learn in later lectures, do not click because there's no moving parts to clack. One must disassemble a mini contactor relay to see the coil and armature. Upon cracking it open, we see something similar to the internal workings of a contactor. The base carries the stationary portion of the solenoid, the coil, and a pair of return springs that are maddeningly hard to properly realign when you reassemble the relay. Notice the shading ring. The coil is meant to be energized by 120 volts AC. The inductively linked shade ring keeps the armature engaged during zero crossing of the AC waveform and keeps audible hum to a minimum. The top portion contains the contacts, the contact carrier, and the armature. When de-energized, the return springs push the armature away. When energized, the coil pulls the armature into it and the associated contacts change states. Here's an octal-based ice cube relay inside the base. The ohmmeter indicates the coil has a resistance just shy of 1.7 kiloohms. If this coil was shorted, opened, or damaged, it would indicate a different resistance or show visible signs of abuse upon inspection. When in its deactivated state, the ohmmeter indicates there is a connection between the common and the normally closed side as expected. When manually triggered using the button on the front, the ohmmeter indicates the normally closed switch has opened. When in its deactivated state, the ohmmeter indicates there is no connection between the common and the normally open side as expected. When manually triggered using the button on the front, the ohmmeter indicates the normally open switch has closed. Ice cube relays sometimes feature an indicator LED on the face to facilitate troubleshooting in a dimly lit or cramped electrical cabinet. Additionally, sometimes the manual trigger button or tab can be locked into place to facilitate troubleshooting or force an input. Here's a mini contactor relay. The ohmmeter indicates the coil has a resistance just shy of 380 ohms. If this coil was shorted, opened, or damaged, it would indicate a different resistance or show visible signs of abuse upon inspection. When in its deactivated state, the ohmmeter indicates there is no connection between the 1-3 and 1-4 terminals of the first normally open switch as expected. When manually triggered using the plunger on the front, the ohmmeter indicates the normally open switch has closed. When in its deactivated state, the ohmmeter indicates there is connection between the 2-1 and 2-2 terminals of the second normally closed switch as expected. When manually triggered using the plunger on the front, the ohmmeter indicates the normally closed switch has opened. Similar to their big brother, the contactor, mini contactor relays sometimes feature an access port on the side to allow a mechanical interlock between two relays in close physical proximity. The mechanical interlock may be as simple as a plastic peg or as complicated as a separate interlock unit that prevents the travel of one relay's contact carrier if the one it is mechanically interlocked to is already energized. This can prevent two mutually exclusive conditions from occurring inside an electrically controlled system's logic. One does not simultaneously go forward and reverse. Not only does this not make sense, it constitutes a phase-to-phase event in a three-phase AC electrical system, an event characterized by an arc flash hotter than the sun and a lab instructor whose anger is hotter than 10,000 suns. The mechanical interlock prevents this most heinous of actions from occurring. Now that we've got a good look at relay hardware and functionality, let us now discuss general specification of coils and relays and highlight some points of interest before we close up shop. Similar terminology is employed for contactors, so this might be a review if you already watched the contactor lecture. The rated voltage of a relay coil must be matched to the control system voltage. A coil designed to run on AC cannot be used on a DC system, even if the DC voltage is much lower. A coil presents both resistance and inductive impedance to an AC waveform because of the changing voltage waveform. A DC waveform only experiences the resistive component, and current draw will be exceptionally high and damage the coil. If one must interface two systems employing different voltage levels, for example, a programmable logic controller with a 24-volt DC output and a 120-volt AC relay coil, either one must exchange the programmable logic controller with one capable of supplying 120 volts AC output to directly operate the coil of the relay, or find a means of translating these two different voltage levels and flavors. Typically, such interaction occurs inside an interposing relay, basically a relay that translates one magnitude of input to a different level of output. We'll discuss both programmable logic controllers and interposing relays in later lectures. In addition to rated voltage, coils have a pickup, hold-in, and dropout voltage. A pickup voltage is the minimum amount of voltage necessary to overcome the at-rest spring or gravitational resistance of the armature. The hold-in voltage is the minimum voltage necessary for the coil to maintain the armature in the activated position once it has been activated. As can be expected, the hold-in voltage to maintain a position is a little less than the pickup voltage necessary to initiate movement to a new position. Finally, the dropout voltage is the amount of voltage below which the coil just returns the contacts to their deactivated state. AC coils are known to experience an inrush current at the moment they're energized, substantially greater than their sealed-in current once the armature has stabilized positions. Finally, given the coil's operating principle is that of magnetism, when current through it ceases, the magnetic field collapses in an effort to keep current traveling in the same direction. This sometimes results in a voltage spike that can damage equipment. Sometimes the means of suppressing this voltage spike is included internal to the coil or must be externally attached to it. As mentioned previously, DC coils with suppression means are polarity dependent. The mechanical linkages, springs, and contacts internal to the relay must be periodically inspected for proper operation and signs of mechanical wear. Misalignment of the contact carrier, spring, lever, or foreign obstructions will prevent movement of the contacts. Silver alloys typically form the conductive contacts because oxides of these alloys are also conductive. Closure of the contacts should ideally be as rapid as possible. However, contact bounce at closing can be problematic for the resolution of logical states inside the control system. It is for this reason some relay contacts are bifurcated or split down the center, minimizing bounce or chatter at closing. Similar to a contactor, the The contacts of a relay have three typical ratings depending upon application: make, break, and continuous current carrying capacity. Inductive loads like motors experience an inrush current several times their normal current draw. Similarly, pilot devices like coils of contactors, other relays, and solenoid-controlled valves experience an inrush. Relays switching these loads must be sized to accommodate this phenomenon during closure and open. One last activity before we bring this lecture to a close. This is meant to be a thought experiment and test your knowledge of what we've thus far discussed. No calculator is necessary, only your consideration. Relays are part of the control aspect of a system. You should understand that when the coil of a relay is energized, the associated contacts change to their opposite state. As we'll learn in later lectures, the associated contacts, although physically part of the same relay, can be electrically all over the map. The coil for control relay 1 could be in the second rung of a ladder logic diagram, and the first set of associated contacts could be in the 7th rung, while the second set of associated contacts could be in the 15th rung. I'll show you some super handy organizational techniques in later lectures on ladder logic diagrams, but a simple technique in keeping your house clean is to assign a name to each associated contact based off the control relay. If control relay 1 has 2 associated contacts in use, the coil is called CR1. The first set of associated contacts is called CR1A, and the second set of associated contacts is called CR1B. You could also call them CR11 or CR12 or anything to distinguish them and make plainly evident that CR1 controls the states of these particular contacts. You'll see in later lectures, I sometimes go to the trouble of actually color-coding the coils and the associated contacts. Here's the conceptual exercise I'd like you to ponder. What if the signal used to energize a relay coil was delivered to the coil through one of the normally closed contacts associated with that relay? Can you predict what would happen? Think about it. No math, no calculations. Consider a relay with a coil designed to operate at 12 volts DC. What would happen if we took a 12-volt DC source and placed the normally closed portion of the CR1A contact in series with the CR1 coil? Would the coil energize? What would happen if the coil energized? What would the associated contacts do? What would happen to the associated contacts if the coil de-energized? Can you predict what would happen? 5, 4, 3, 2, 1. Here's what happens. You create a buzzer that will provide no end of mirth or annoyance to those in immediate proximity. Why is the relay behaving in this manner? In its de-energized state, the normally closed contact allows current flow to the coil, and the coil is energized. When energized, the associated contacts change to their opposite state, and the normally closed contact opens, de-energizing the coil. When the coil de-energizes, the normally closed contact returns to its deactivated state and energizes the coil. Repeat as necessary. You would not ordinarily wire a relay in this fashion unless you wanted to create a buzzer. However, I really get a kick about this particular activity because it directly highlights the relationship between and the function of a relay's coil and their associated contacts. You'll notice 2 important points about this activity. 1, the repeated open and closure of the relay is occurring at a natural frequency, implying there is only so fast a device composed of moving parts can move. We'll learn in later lectures about solid-state relays, relays with no moving parts that can rapidly turn on and off at high frequencies, not limited by the physics of moving objects. 2, notice the arcing that is occurring on the contacts. As mentioned previously, a coil contains magnetic energy. When current through it ceases, the magnetic field collapses, propels current in the same direction. This DC coil does not have any means of suppressing this arc. If this buzzer went on for any length of time, we'd damage the contacts. This wraps up our brief introduction to the relay. We'll be making use of this device in later lectures as the principal logical element of an electrically controlled system. Logical operations include, but are not limited to, controlling the motion, making decisions, and communicating information. We'll learn in later lectures how relays can make these logical functions possible. In conclusion, this lecture took a brief look at the relay. We identified the terminals, switches, contacts, and coils, and examined the functionality of a plug-in ice cube relay using a base, and an industrial mini contactor relay. Additionally, we discussed general coil and relay specifications, and had some fun making a buzzer out of a relay. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.